Hey there, welcome back to the next lesson in higher mathematics. So continuing geometry now, and we're taking our knowledge of 2D shapes and we're taking it into the next dimension, into three-dimensional shapes. So let's take the lesson plan for today. So first of all, we're looking at prisms, probably the simplest or one of the simplest three-dimensional shapes we can work with. We'll see what defines a prism and what properties does it have. Then we'll look at what are known as polyhedra, which are kind of like a next step up, related to polygons, hence, similar names. Then we'll look at spheres and cones, so curved shapes, curved three-dimensional shapes, and we'll see, okay, how can we deal with those? Because obviously it's going to be a bit trickier than ones that have very, just flat sides. We're going to look at a frustum, which is more uh, like a composite shape, like other shapes we've seen, but we're taking apart away. We'll see how that works, um, and we can use a lot of the knowledge we've already developed to then deal with them. And then we're looking at surface area and volume, so key properties of three-dimensional shapes. Surface area being the area all around the surface of the shape, as you might expect. Volume, the space that is contained, the three-dimensional space contained inside the shape. How do we calculate what those things are and the units and things like that? So let's start off with prisms. So a prism, as we saw last time, we can take a shape and essentially push it through a perpendicular dimension in order to take it up to another dimension. So like here, we start off with a zero-dimensional point. We drag that across in one dimension to produce a one-dimensional line. We then sweep that up another perpendicular dimension to get a two-dimensional square. And now we can do this one more time, taking that 2D shape. And this takes a little bit of imagination now, pushing that square through the screen to create a three-dimensional cube here. And so, yeah, like I said, 3D shapes today, it's going to require a bit of visualization here, to see these three-dimensional shapes, but I've tried to make it as easy as possible. So this would be like our standard unit for a volume. So we have um, a distance cubed in this case, hence why it's called 1 meter cubed and not 1 meter to the power 3. We use it because it means we call it cubed because it represents a cube here. And if we had say 1 centimeter cubed, that's the same thing as a milliliter. So uh, that's the relationship between milliliters or distance cubed. It's basically both representing volume. So say if we had a rectangle like this, well, say rectangle, a cuboid, and we want to know how much volume is inside this cuboid. It's you can basically see how many lots of these 1 meter cubed units are going to fit inside it. So we put one in there like that, and we can continue to put in more and more and more until we cover up the entire base, and then gradually put in new rows until we get to the top. And so you see here we've got a convenient shape here where it fits in perfectly, and we can see what then the volume of this is going to be because it's 3 by 4 by 8 meter cubed blocks. So it's a total of 96 of those meter cubed blocks, and so it's 96 meters cubed is what the volume of this shape would be. So again, that's all good and well when we've got a nice cube or cuboid like shape. We need to think, okay, how can we then extend this to work for all shapes? So a prism is one of the simplest 3D shapes to work with, as they're simply a two-dimensional shape that has been pushed into the third dimension, just like what we did there with the square. So suppose we have a triangle, we can then make what we would call a triangular prism by taking that triangle, and here again, imagine pushing that through the screen to create uh, that volume that it's going to sweep out will be a triangular prism. And you see, it's just it's just that two-dimensional shape pushed through. And if you sliced it vertically at any point, it would essentially just produce the same triangle because it's just that same two-dimensional shape throughout the whole like tube shape. So that's a triangular prism, but we can do this for any shape. So say if we had like a pentagon, we could make a pentagonal prism, pushing it through the third dimension, and that area that sweeps out. We could have like a circular prism doing the same thing. A circular prism is more commonly known as a cylinder, so it has a special name, that one. Um, so that's the most common shape you'd think of when I think of a tube shape, but all prisms are kind of like a tube. And we can even do this with an irregular shape. So you see this little L shape I've got here. I could also push that through a third dimension. And you see the volume that it sweeps out is then the three-dimensional shape. And that would also be a prism. So that's what a prism is. It's where it's just a two-dimensional shape that's been pushed through a third dimension like that. So now let's look at polyhedra and how does that differ. So a polyhedra is a three-dimensional shape where each of its faces are polygons. Our triangular prism could be dismantled into two triangles and three rectangles. So we'd take our triangular prism we have here. You see, if I imagine dismantling it like this, there's the two triangular faces on each side and then the three rectangles going round. So you see, all prisms are polyhedra because you're going to have two polygons at each side and then a series of rectangles going around, which themselves are polygons. But not all polyhedra are prisms. You know, a simple example of one that wouldn't be a prism is a tetrahedron, which is basically made up of four equilateral triangles put together. And if I dismantle that, you see it's essentially, yeah, just four equilateral triangles like that, which is a type of pyramid. So what is a pyramid? So a pyramid is a polyhedron that has a polygon base and then some number of triangular faces connected to each side of that face that would then come up to a point. So we've seen one example already, the tetrahedron, which you could also refer to as a triangular based pyramid. Because you see here the base is a triangle and then you've got then a series of other triangles coming up to a point. The most common type of pyramid we'll look at is known as the square base pyramid, which unsurprisingly has a square base. So we have a square base laying flat and then a series of four triangles coming up to a point. But theoretically, you could have any base pyramid. You could have, say, something like this. Any polygon, you get an appropriate number of triangles and put them around the edges. In this case, a pentagonal pyramid. And a pentagonal base pyramid. So more often than not, you come to a square base pyramid or perhaps the tetrahedron. You don't really encounter many other types of pyramid. If you dismantle these, yeah, you can then clearly get an idea of what the different faces look like. So you have that base, which is some polygon, and then a series of triangles where the number of triangles match the number of sides. So that's pyramids. Let's look at spheres and cones. So we have a sphere here. Kind of tricky to visualize a sphere. I've put like these like lines of like longitude and latitude across the sphere, so you can kind of get an idea. But imagine a sphere is a ball shape. I suppose you're familiar with that. So, like a circle, a sphere is the locus of all points that are some constant distance away from a particular point. But it's just extended to a three dimensions. So it's not just on a two-dimensional surface, but in three dimensions, you know, going some distance in all directions, that creates a sphere. And you know, it's going to have properties like a radius. If you cut the sphere at any point that goes, you know, through the center, it's gonna essentially produce a circle, you know, with the same radius. You know, if you cut somewhere else, it would produce a circle with a, you know, a different radius. But the main other shape relating to the sphere that we need to be familiar with, which is what's known as the hemisphere. So that's when you literally just cut a sphere in half, you create a hemisphere. You might be familiar with in terms of like the Earth, like the northern hemisphere, southern hemisphere. It's basically the top and bottom half of the sphere. So yeah, you want to be familiar with that term as well, hemisphere. So we have a cone. A cone is a shape made up of a curved surface and a circular base. So it's defined by its radius and its height, or perhaps sometimes its slant height, which is this height going like diagonally, like a slant, hence why it's called slant height. So we need the appropriate information. Say if we're trying to calculate surface area or volume, we're going to take a look at that soon enough. But using some basic trigonometry, we can kind of convert between the slant height and the regular height. We haven't seen that yet, but we will do soon enough. So cone can be described as open or closed, depending on whether it includes the base or not. So a closed cone would be, well, one like this where it has actually got a circular base on it. Or if there was no circular base, then it's described as open. Imagine like an ice cream cone where it's just an open cone and you can put your ice cream in it. So yeah, you might want to make sure you're familiar with that, and be very careful when you're doing questions with a cone, because you might be trying to calculate surface area, and if it's open or closed, it's going to determine how much area it is. Like, are you going to count that bottom or not? So yeah, you might want to be careful with that. That's a silly error that could happen. So let's look at frustrums. What is a frustrum? So it's a frustrum is one of those shapes that can often be overlooked, or sometimes a lot of students aren't aware of what a frustrum is, but maybe you've encountered these kinds of problems working with frustrums before. So a frustrum is the portion of a three-dimensional shape that lies between two parallel planes. So a plane is like a flat surface. So it's like you're taking two flat surfaces and you're cutting straight through a shape like that. And the piece in between those two surfaces is then what's known as a frustrum. So that's what a frustrum is in the general sense. But at GCSE level, we only really look at a few particular cases really. Um, Typically applied to pyramids and cones is what we focus on at GCSE level. And so you take something like a pyramid here, and you can imagine, well, just slicing horizontally to that base of the pyramid, something like this. I've just sliced right through, and I take that top part off, and then what's left here, this is known as the frustrum. And you can see it's made up of two polygons, matching the base of the original pyramid. So say this one being a square base pyramid, you've got a big square base, and now you've got a little square on top, and then you have a series of trapeziums essentially going around the outside. Because think about it, a trapezium is basically a triangle with part of it chopped off, isn't it? So you can kind of see how we would calculate something like surface area uh, later on. So we're just looking at what the different types of shapes are first before we take a look at surface area and volume. So another type of frustrum we can do basically using a cone. Um, and it's going to be more of like a circular frustrum. So similarly, we get a cone and we cut horizontally to the base, and we take off the top part of the cone, and what's left here is then like a circular frustrum. See, and it's got two circle sides, for the base and the top, and then one continuous uh, curved shape that goes around, which you might be thinking how we'd calculate the area of that. It's actually going to be calculated as the differences between two sectors. That will make more sense as we look into how we calculate the surface area of a cone soon enough. So, speaking of which, let's take a look at surface area. So, surface area kind of is what it says on the tin. It's the area around the surface of a shape. So, that can be tricky for shapes that are curved. For ones that are flat, like the prisms, polyhedra, or any other shape with flat sides, I think those are the main ones. We can essentially try and dismantle the shape into its various 2D shapes, calculate the areas of all those 2D shapes, and then add them up. As simple as that. So I say simple. The hard part is being able to do that dismantling in your mind. Um, so I would often encourage you to not do it in your mind. Try and maybe you at home, from paper or card or whatever, you can construct these various different shapes, and you can kind of play with them and dismantle them and whatever, to then build up that sort of way of visualizing them. If you're not so good at just like some people, you can just see it. You can see it, and you can kind of move the shape around in your mind and dismantle it, and that's great. So this will often be very easy for those people. But if you're not, you want to develop that spatial reasoning through working with physical things, or perhaps online programs where you can visualize three-dimensional shapes, something or the other. Right, so here, let's look at calculating the surface area of a prism. So recall a prism is made up of two copies of a polygon and then a series of rectangles that are joining up each of the edges of those polygons. So the edges are, just the sides. So the surface area will equal the sum of all the areas of those two-dimensional shapes. So for example, if we take a pentagonal prism, and we're given some information like this about it, how do we calculate its surface area? So first of all, let's just look at the pentagon at the front, because we already know how to do that. We've done this before. we can divide it up into triangles like this. Each triangle is going to, base times height divided by 2. So 4 times 3 divided by 2. And 5 of them will make up that pentagon face. So that pentagon is going to be called this. Okay, what about the rectangular side? So we see there's a depth of 2 centimeters. The side is going to be 4 because you see that the side length of the pentagon is 4, and that's going to be the same all the way around the pentagon. So we see, again, you've got to almost be able to like visualize. Imagine yourself kind of going round to the side of the pentagon and looking at it from that side. You can see this is going to be a 2 by 4 rectangle. So it's going to be basically 4 centimeters times 2 centimeters. And now let's just add it all up. So we've got the area of the pentagon, we've got the area of the rectangle, we've got 2 pentagons, the one on the front and the one on the back. So we times that by 2. Then the rectangles, we've got 1, 2, 3, 4, 5 going all the way around, attaching to each of the 5 sides of the pentagons, So we get 5 of those. And if we add all that up, that will give us the surface area. So now we know what the calculation is. We've just got to do the calculation and be mindful of your units and stuff. This one comes out to perfectly 100 centimeters squared. So because it's an area, surface area, it's always going to be a distance squared. So just be mindful of that with your units. Don't put down 100 centimeters or something like that. It's going to be 100 centimeters squared. And you can see that in both terms of this equation, you're getting centimeters times centimeters. So that's where the unit comes from. Right, so if we calculate the surface area of a frustum this time, we do it in the same way we do many other shapes. Remember that frustum consists of copies of a polygon on, the base and the top, typically square-based polygon, square-based pyramid, isn't it? So it's going to be squares. The one bigger one smaller one, and then a series of trapeziums going around the edge. So say we've got a pyramid like this with a side length of 7. So this is a square-based pyramid. What you'll most likely encounter. Imagine the frustum, we're chopping off the top part like that. And so now we can see we've got enough information here. So that 8 centimeters is like the slant height going up the side of the slanted side of the pyramid. So you can see that's a trapezium there. So we can use our formula for the trapezium where we've got the sum of the long side and the short side, 3 plus 7. We do half of that times by the height. So we often think of that as the vertical height, but in the sort of like domain of that trapezium, that slant is its height, isn't it? So that trapezium, kind of got to imagine taking that off and like laying it flat on a surface, and then you can kind of see. So when we say height, it doesn't necessarily mean just vertical, like in this vertical relative to this 3-dimensional shape. It might be vertical on the surface of that shape. I hope that makes sense. So yeah, imagine taking that trapezium off and laying it flat so we can, and then we're essentially working it out in the same way we've done before. And you'll find that comes to 40 centimeters squared. And the surface area, therefore, will then be this. So we've got 4 lots of that 40. So 4 times 40, because there's 4 trapeziums going around the edge. We've got the base, which is going to be 7 times 7, because it's just a square. The top, which is going to be 3 times 3, because it's also a square. So you see there, 4 lots of 40 plus 49 plus 9 gets us the full area of 218 centimeters squared. That's the full surface area of the shape. So you just got to make sure you've just accounted for all the different sides. And there you go. So let's look next at a cylinder. How would we calculate the surface area of a cylinder? So this one, it's relatively intuitive that we can actually just prove it right here. So you see a cylinder is defined by 2 lengths. We've got the radius of the circular bit on the top. That defines the circle. And then we've got the height, which is like the distance we're pushing that 2-dimensional shape through. So that creates this prism shape. So we've kind of got a different orientation this time. Rather than thinking of it as a circle like that pushing this way, we've got a circle like this coming straight down. So it's still a prism. So the surface area can be found by essentially like unraveling the shape. So this is like a closed cylinder. We've got 2 circles on the top and the bottom. And if we imagine now that round bit, imagine unraveling that out. And so we've got the 2 circles, and then we've got this bit that's unraveled out. You see it's going to be a rectangle. And if the cylinder is closed, then we've got those two circles that we need to calculate. So it might be closed or it might not. Like say if the question is talking about like a tube, like an open tube that maybe water is running through, then you don't need the area of those circles in the end. Um, you just maybe you're calculating just the area of the actual tube itself. So just be mindful of that. Kind of like the cone, it depends on whether or not you need those. Whether it's open or closed. So the circles is just going to be 2 pi r squared. Pi r squared each, and there's two of them, so it's 2 pi r squared. So the curved bit that is now laid flat as a rectangle. How do we work that out? Because we've got the height is h, but what is the length going to be? We don't know what that is. Well, we can work it out because think about it. When we unravel this, that long length is basically what went around the circle, isn't it? Like when we wrapped it around that circle. So that length is going to be the same as the circumference of the circle. So it's 2 pi r. And so therefore we can calculate the curved area now, 2 pi r times h, 2 pi r h. And so if we wanted then the total surface area of the circle, we could just add those two together. And what I'll do is I'll take out the common factor of 2 pi r, and on the inside you're just going to get r plus h. So we've got like a little formula there if we wanted for, the circle parts, the curved area, then the overall area. But you see, it's all very intuitive. You don't really need to memorize formulas for this kind of thing. Some of them we do. We really do, because there's no other way of doing it. Speaking of which, like a cone, for example, can be a bit trickier. So the proof of the surface area of a cone, I'm going to leave for more like the bonus material, but we need to be aware of what those formulas are. So surface area of a cone. So again, like try and dismantle the shape out. So we've got this one continuous curved area, and then a circle on the bottom. So given the radius, we know the base is just going to be pi r squared. Now, given the slant height, so that's not the direct vertical height, but the slant going up the side of this cone, we need to unravel the cone. So we could pop off the bottom of the cone like this, and imagine unraveling this out. So this is something that you can quite easily make with, say, like a piece of paper. If you have a sector shaped like this, and you can wrap it round so that those two sides that I've labeled S there match, you see it will create a cone, and you can sort of see how this unraveling would work. So we lay it flat like this, and how would we calculate the area of that sector? Because it is a sector. It's basically like a fraction of a full circle, but we don't know what proportion is. We've got the slant height is essentially forming like the radius now of this big circle. So the surface area would be basically pi s squared. But then we need some proportion of that, which would normally be given by the angle, but we don't know what that angle is. And it turns out you don't, at least in this case, you don't actually need to know that angle. It can be worked out, and it's a proof. This is kind of a proof that we can do in detail, and you could follow it with just a GCSE level of understanding. But I'll put that in the bonus material. Yeah, if you're interested in where this comes from, but that sector that makes up the curved area of the cone is just simply pi rs. So pi times by the radius of the base times by the slant height of the cone produces the area. Beautifully simple little formula there, pi rs, and that gives you the area of this quite complex area, really, of a cone. Yeah, which is great. So that's a formula we need to be familiar with. So surface area of a frustum from a cone, the frustum made from a cone, we need to take a slightly different approach. Okay, so we've got something like this, and we chop off the top, and we've been given these lengths. How would we calculate then the surface area of this frustum? So we can use what we've just learned about a cone, because you can see this is basically a big cone with a smaller cone chopped off. So if we can find the difference between those curved areas, which we just found out is pi times by r times by the slant height. So for the large cone, the big cone, including that missing bit, you can see the slant height's 11 and the base radius is 5. So we've got pi times 5 times 11 gets us 55 pi centimeters squared. The smaller cone on top, the bit that's been chopped off, You see the base is 2 centimeters and the slant height is 6. So we get pi times 2 times 6 gets us 12 pi centimeters squared. And so therefore the curved area of the frustrum is just going to be the big one minus the small one gets us 43 pi. And so now if it's like an open frustrum, like a closed frustrum, sorry. So we've got the circles on the top and bottom, which typically we will when we're dealing with frustrums. We can work those out quite simply because the base is just going to be pi times 5 squared, which is 25 pi. The top is going to be pi times 2 squared, which is 4 pi. So now we've got 43 pi plus 25 pi plus 4 pi, gets 72 pi. And if we wanted a specific numerical amount, we could then plug that into our calculator. But you see there, we've managed to keep the exact value by keeping it in terms of pi. So yeah, good to be familiar with doing that because you will be asked things like that. So let's look at the surface area of a sphere. So a sphere is a more complicated shape in that it can't be laid flat. Like with these other shapes where we could just kind of unravel it and then lay it flat. A sphere, if you kind of imagine that in your mind, there's no, I mean, because it's completely closed in just one surface, there's not multiple surface that we can pull apart. It's just one surface and it's completely curved around. There's nothing we can do. The formula for the surface of a sphere is 4 pi r squared. This requires some very advanced mathematics, far beyond GCSE level to prove this. I've tried to give like a very simple visual proof in some of the bonus material, but yeah, there's only really so much I can do with this because this is like very much like university level mathematics to prove like say the surface area of a sphere. But that's the formula, 4 pi r squared, that we need to be familiar with. So let's look now at volume. So that's the three-dimensional space inside the shape. So recall that the volume of a cuboid can be calculated by multiplying its width, length, and depth. So this should be very straightforward. Like we've seen from the very definition of what volume is, little centimeter cubed space blocks, and we've got 3 by 7 by 10. Where we can just multiply all that together and we get 210 of those little blocks would fit in that space. Now, if we look at it in a different way, so imagine if we didn't have all those lengths. So imagine it like this: if we just had that length 7 and was given the area of the front, which is 30 centimeters squared, we could calculate this by visualizing it like a prism. So we have that 30 centimeters squared area, and then we're pushing it through that third dimension, and the volume that's going to sweep out is going to be that area times by the distance you're pushing it through. So 30 centimeters squared times by 7 gets us 210. So you see it works out same value in this case. But there's a reason why we're looking at it like that way, because we can use this knowledge to then calculate the volume of any prism. If they're simply like some polygon, or not even necessarily a polygon, but some kind of two-dimensional shape pushed through into the third dimension, we can work out the volume in a similar way. So take something here like a regular heptagonal prism. If we know the area of the heptagonal cross section, just that heptagonal face on the front, and we can times it by the length that we're pushing it through. So if we have the appropriate information like this, we've seen this before, we can calculate the area of that polygon. It's going to be that what is sometimes known as the cross section. If you just chop down, and if you imagine chopping at any point like vertically down, you're going to get the same heptagonal shape. That's what's known as the cross section. So you see that triangle is going to be 3 times 4 divided by 2. We've got 7 of them make up the heptagonal face, so that cross-sectional area is going to be equal to this. And then we're taking that area and you're pushing it through into the third dimension. And so the volume is going to be that 42 meters squared times by the 11 meters you're pushing it through, creates 462 meters cubed. So it's like saying that this area is equivalent to 462 1 by 1 by 1 meter cubed blocks. Taking it back to the our like very definition of volume. We can work out a cone. A cone is a bit more of a complicated volume to calculate. Can't really be interpreted as a two-dimensional shape sweeping through a third dimension. So how do we do that? There is a proof that is a bit tricky. for this. Again, I've tried to give like just a rough sort of visualization of this in some of the bonus material if you want to know why this is the case. But really, we can calculate the volume of the prism taken from the base of that cone or pyramid. So you're sweeping that shape up, and you see here it creates a cylinder shape, which we can calculate from R and H. So that base area of pi r squared times it by H gets the cylinder, and this thing cone shape within that cylinder will work out to be exactly 1/3 of that. It's interesting how it just comes out to exactly 1/3 of that prism that encloses it. And we can do the same thing for a pyramid, which is really handy when we're doing something with a frustum. So if we're calculating the volume of a frustum, it can generally be more complicated, but it's definitely within the scope of GCSE math, and we can solve it by making these simple observations. So that okay, we've got a pyramid, we're chopping off the top part of the pyramid, and so we need to know where that is and what the dimensions of that is. And then notice that the original shape that's removed is the same shape but just a different size, so it's like a smaller version of the bigger pyramid. So we could calculate the volume of those two pyramids. We've got the big pyramid, including that bit on the top that's been taken away, and then we've got the little bit on top, which is like a small pyramid. So like what just like the cone, we can take the base of that pyramid. So say the big pyramid, which is going to be 5 times 5, and then times it by the full height, which is 6. So that's going to be like the cuboid, the prism. Cuboid is a prism, isn't it? The prism that encloses that pyramid. And then the volume of that pyramid is just simply 1/3 of that. And we can do the same thing for the little one on top. The base is going to be 2 times 2. We times it by the height of 3, which is then creating another cuboid that encloses that pyramid, and that pyramid will then just be simply 1/3 of that volume. So it's really nice. That it's not very difficult to work out at all. So the full volume is going to be that big pyramid minus the little pyramid, and we will work that out to be 46 meters cubed. So by making that observation that with essentially the difference between two pyramids is what's the volume of this frustum, we can calculate that from the understanding of a pyramid. So we've got the formula of a pyramid, but like I was saying, you don't really need to remember a formula. You just need to remember it's simply like 1/3 of the prism that encloses it. And if you get good at sort of visualizing how that works, then it's very straightforward. So let's look at a sphere. Again, sphere is quite a complicated shape. There's no real satisfying way I can really prove the volume of a sphere at GCSE level. So it can be the difference between the volume of a cylinder enclosing the sphere and two cones with a radius and height equal to the radius of the sphere. Why that would be the case might be very hard to sort of see, but I've given like a little visual proof in the bonus material that might help if you want to have a rough idea where the formula for the volume of a sphere comes from. But yeah, like again, this is very far beyond GCSE level, so you don't. It's okay if you don't understand that, and you don't need to understand it. All you need to know is that the actual formula for the volume of a sphere is 4/3 pi r cubed. So again, beautifully simple formula, like all the ones relating to spheres and circles. It just depends on the radius. So if we know the radius, we can calculate the volume of the sphere using this formula. And that's it. That's the last shape to consider. So let me leave you with this interesting fact about polyhedra. So remember polyhedra, any three-dimensional shape that's just made up of a series of polygons, fitted together. And there's a neat little equation that relates the number of vertices and edges and faces. So we have various faces. The faces meet at edges, and then those edges meet at vertices, points, just in case you're unfamiliar with what those terms mean. And you find we have this little equation that will always equal 2, which is basically this. The vertices minus the number of edges plus the number of faces always comes out to 2. And you can test this for a bunch of shapes, like a cube, 8 vertices, 12 edges, 6 faces, comes out to 2. A tetrahedron that has 4 vertices, it has 6 edges and it has 4 faces, comes out to 2. Hexagonal prism, 12 vertices, 18 edges, 8 faces, still comes out to 2. And this is all the same for every single polyhedra. So it's really simple, but amazing result that just applies to any polyhedra you could possibly come up with. It's really, really interesting. So here we go. This is our takeaways for today's lesson. So we've done everything we can do with three-dimensional shapes now, all the different types of shapes, calculating surface area and volume. So next time, so I've mentioned a couple of times, oh, we need a bit of trigonometry for this, bit of trigonometry for that. So now we're going to actually move on to trigonometry, which you see can have uses in two-dimensional and three-dimensional shapes. It has uses in graphs and coordinates as well and things like that. Very important subject, trigonometry. So I'll see you next time for that.